Hi guys, I'm going to go over the first unit review for you before you take the first unit exam. So this first part, we're trying to identify the difference between an element, a compound, and a mixture. Probably the biggest thing, the biggest indicator, if it's an element or a compound, it's going to have a symbol or a formula with it, okay? And if it's a mixture, it will not have that, all right? So the difference between a symbol and a formula, well, a symbol only has one capital letter. If you have a formula, you'll have at least two capital letters. So that's really what you have to look at here. So water, notice two capital letters. That's going to be a compound, all right? It's got a chemical formula. Trail mix, no formula, can have different stuff, so that's a mixture of things. Same thing with salt water. You can have different salts, you can have different amounts of salt in there. That makes it a mixture. Lead, Pb, one capital letter, that's an element, and it's found on the periodic table. Chocolate chip ice cream, same thing, mixture. Calcium chloride, two capital letters, calcium and chlorine, that is a compound, two elements bound in a fixed ratio. Potassium, that's an element. Brass, believe it or not, is a mixture. A lot of people think brass is an element, but it's not on the periodic table, and it's not even a compound. It's a mixture of two elements, nickel and, or no, I'm sorry, it's zinc and copper. And so the varying amounts of zinc and copper gives it different properties. So that's the first one. Okay, label the following particles either solid, liquid, or gas. Okay, obviously this is going to be the solid because notice the particles are packed in real tight, so they have a definite volume and a definite shape. They sit there and kind of vibrate in place. This one's trying to demonstrate a liquid because notice they're still kind of moving, but they're still clumped together, but they're able to flow past one another. And this is going to be a gas because they're spread far apart, able to bounce off the walls of the container. And so it's saying, giving an example, well, we can use like even the same substance. So let's say we want to use water. So liquid water is a substance. Well, when it's a solid, we call it ice. And then when it's a gas, you call it, could be steam or just water vapors, whatever, depending. Okay, so pretty straightforward. Which particles have the least kinetic energy? That's going to be the particles in a solid, okay, because they're just kind of sitting there. The greatest, that's the gas. And remember, when we're talking about kinetic, that's moving around. What distinguishes atoms of one element from atoms of another? This is the only thing, the number of protons in the nucleus. They can have the same number of neutrons, they can have the same number of electrons. The protons will be unique. How do you calculate the number of neutrons in an atom? Well, you remember that the atomic mass is equal to the number of protons plus the number of neutrons. So if you know the mass and you know the atomic number or the number of protons, all you do is you subtract the number of protons from the mass. That gives you the neutron number. How do you calculate the number of electrons in an atom? Well, normally the number of protons is usually going to be equal to the number of electrons, okay? So usually atoms like to be neutral, but if you have a positive ion, which is also called a cation, then the number of protons is going to be greater than the number of electrons. If you have a negative ion, which is an anion, the number of protons is less than the number of electrons. Okay, so you just have to look, is the atom neutral? Is it an ion with a positive or negative charge? And that will tell you what you have to do with the electron number. How are isotopes of a given element different from one another? They have different masses. Um, and why? Because they have different numbers of neutrons. Okay, how are they the same? They have the same number of protons. How do you calculate average atomic mass? So this is the formula. So you take the mass of the first isotope times its percent abundance plus the mass of the second isotope times its abundance plus the mass of the third times its percent, and you keep going until you get to all of them. That's going to give you the average mass. Most of the volume of the atom is empty space. Okay, so most of the atom is nothing. And then, so you have to remember that most of the volume is taken up by the electrons, which are spread way far apart. Almost all the mass, though, is in the nucleus, where you have the protons and the neutrons packed in there. So all the mass is in the nucleus, but that is tiny, 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 and very dense. The majority of the atom is nothing. Okay, let's fill out one of these sheets. I don't know why we have atomic mass on here twice, because we have mass number, atomic mass. We're just going to get rid of that last column. Okay, and so filling this out, I look at my periodic table, I notice silver is AG number 47. I want to put hyphen 108 so the mass goes after. Atomic number is the one written down below, 47. The mass is the number on top, the superscript to the left. The atomic number and the number of protons are always the same. Protons plus neutrons is the mass, so what number plus 47 is 108, or essentially 108 minus 47 should be 61. And then there's nothing indicating this thing has a charge, so the protons and electrons should be equal. Next one. We've got nickel 59. So the atomic number there is 28. Mass is 59. So I have 28 protons. One number plus 28 is 59, should be 31. And nothing indicating this thing had a charge, 28 electrons. Okay, carbon 12, so that means symbol is C. 12 is the mass. 6 is the atomic number of carbon, looking at the periodic table. So atomic number is 6, mass is 12. 6 protons, 6 neutrons, 6 electrons. Okay, the next one, aluminum hyphen 27. And so atomic number is 13, mass is 27. There are 13 protons, 14 neutrons. Now notice this has a net charge of 3 plus. This is an ion. That tells me that the protons and electrons are not the same. Because the protons, is 3 plus, that means they have 3 more positives than negatives. If protons are 13, electrons are 10. Finally, the last one here, oxygen hyphen 16. Atomic number is 8. Mass is 16. That means I have 8 protons and 8 neutrons. Notice this is an anion, it's negative. That means I have more electrons than protons. How many more? 2 more. Well, if this is 8, this must be 10. Okay? Average atomic mass. All right, we just did the formula where you do the individual masses, the isotopes times their abundance. That'll give it to you. The only way you can screw this up is you forget to move the decimal place. When you're multiplying percents, you must move the decimal place 2 places to the left. So to set this one up, let's see, 62.93 times its percent, which is going to be 0.692. And then we have 64.93 times its percent, which is going to be 0.308. Multiply and then sum, and you're going to get 63.55, and then label it AMU, atomic mass units. Okay? And look, that answer makes sense because it's between our range, right? And it's closer to the one that is more abundant. I mean, 70% of them are this, so it's going to be closer to 63. So, looks good. Next one, we're calculating atomic mass of rubidium, so same deal. 84.91 times its percent, which is going to be 0.7216. And we're going to sum that. The other one says weighs 86.91. times its percent, 0.2784. Multiply, and sum, and your calculator is going to spit out 85.47 AMUs. Okay, one more of these. Okay, so let's see. The first one is 31.97. It looks like 95% of it's that, so it's going to be 0.9500. The next one, 32.97 and 0.76, so you have to move the decimal 2 places still. So it becomes 0.0076. If you just do 0.76, that means 76%. You've got over 100%. So make certain you're moving that decimal 2 places. Let's see, 33.97 times, and this is 4%, so you still move it to 0.0422. Okay. Multiply, and then sum all these together. 32.06 AMU. Pretty straightforward. Okay. How are wavelengths and frequency of light related? Well, you have to remember the formula. C equals lambda nu. So the speed of light is the wavelength times the frequency. Well, let's just stop and think about this mathematically, all right? The thing you have to realize, C isn't going to change. Okay, C is a constant. So let me give you like this example, right? So let's say, let's just make up easy numbers to look at, and I can demonstrate this. Let's say I'm going to use, let's say wavelength, I'm just going to give a unit of like 3, and frequency is going to be 4, all right? Well, we know 12 equals 3 times 4, all right? Well, let's say I want to change this, and so 12 is not going to change because 12 is constant. Let's say that the wavelength, let's say it goes down, okay, from 3, let's say this goes to 2. And I want to solve for what x is going to be. Okay, well, you guys understand that to solve for x, you divide, right, both sides. So 12 divided by 2, that's going to give us 6. So if this is 6, wavelength went down, frequency went up. So how are they related? This is called inversely proportional. They do the opposite thing. One goes down, one goes up, and vice versa. Inverse proportion. Okay, how do different atoms emit different colors of light? Be specific. Probably the best way I can explain it, this is back from our laboratory exercise with a flame test. Okay, so let's say here I have an electron that is just sitting there happily floating around the nucleus of an atom. What's going to happen is that we're going to energize it. And so we're going to add external energy to it. Okay, so we're going to strike this atom with some external energy. This could be heat, is what we used. You can use light. You can use high voltage electricity. Okay, what's going to happen is that this electron is starting out as what is called a ground state, its lowest energy state. All right, and this electron is going to absorb that energy and it's going to jump up. Okay, and so what it's jumping up to here, these are called excited states. So these are just high energy states. This electron is at an elevated state, okay, and what happens is as that electron jumps up, it has the natural tendency that it wants to fall back down. And as it falls back down, it's going to have photons of light released. Okay, and that's, you get different colors because each element has a unique arrangement for their electrons. They have a unique number and a unique spacing. And so, sometimes they give off just one wavelength that they fall all the way back down, or sometimes they take a number of steps and, set off different, a bunch of different little wavelengths of light, these little packets. And so that's why when we observe them, we see different colors for the different elements. Okay, so here we're calculating the frequency of radiation with a wavelength of 5.5 times 10 to the negative 8th meters. Well, we need that formula, C equals lambda nu. Hopefully you guys know how to use your scientific calculator. The thing you have to realize is that C is always the same number, and C is this, 3.0 times 10 to the 8th meters per second. C is the speed of light in a vacuum, and that's what it is. That is the speed of light. So we just plug in what we know and solve for what we don't. So C is 3.0 times 10 to the 8th meters per second. The wavelength is 5.50 times 10 to the negative 8th meters. Frequency, we do not know. How do you solve for this? Well, you're going to divide by 5.50 times 10 to the negative 8th meters. This goes away. The meters goes away. I enter into my calculator 3.0 EE8 divided by 5.5 EE negative 8. When I do so, I get this, 5.45 times 10 to the 15th and per second or hertz. So you can write it just Hz as hertz, or you could write per second, or you could put second to the negative 1, either one, but this is probably the easiest. Okay, very similar, except for this time we're looking for the wavelength this time. Same thing though. C equals lambda nu. C is always 3 times 10 to the 8th meters per second. This time we don't know wavelength. Frequency is 4.74 times 10 to the 14th hertz, or per second. Okay, I'm going to divide 4.74 times 10 to the 14th per second. The per second goes away, which leaves me with meters, which is good. That is a wavelength. I enter this in my calculator. It's going to look like this. Is probably what your calculator is going to spit out. I do not want that as an answer. If anything goes beyond this decimal place, so within the thousands or thousandths, my expectation is that you will do scientific notation. As you move the decimal place to the right, you realize the power becomes more negative. Okay, and I have to put the decimal after the first non-zero digit. So I'm going to move the decimal to the right 1, 2, 3, 4, 5, 6, 7. So this becomes 6.33 times 10 to the negative 7th, the unit meters. 22, the quantum level occupied by an electron depends upon the energy of the electron. Changes in the quantum level are related to the absorption or emission of energy. The figure below represents 4 lowest energy levels of an atom, so the principal quantum number 1 through 4. The 6 lettered arrows represent changes in energy of an electron. So which of the lettered energy levels involves absorption of energy by an atom? So you guys remember, when it absorbs energy, the electrons become excited and they jump up. So which ones are going up? B, D, and F. Okay, then on the next part says which of the 3 ones involves emission of light. So you remember that it emits light when those electrons fall down from an excited down to a lower energy state. Well, which ones are going down? A, C, and E. Easy. Okay, we're going to do some electron configurations. So electron configuration, orbital filling diagram, and then doing number of valence and the Lewis dots, right? So let's take a look. I'm going to do the electron configuration for each one of them here, and then we'll go and do the orbital filling. Okay, so let's take a look here. Phosphorus. Phosphorus lives right here, and so you remember when we start up here at the top, and remember, we're going to pretend that helium lives right here. It really doesn't, but for this exercise, it's going to make it much easier. And you guys will recall these are the S electrons here. These are the P's. In the middle section, we have D's, and then down at the bottom, we have F. We're not going to deal with D or F right now. So anyway, if I want to do the electron configuration for phosphorus, I start at the beginning, and so this tells me the energy level. These period numbers. So we have 1s, 2, 2s, 2. We go over here 2p. There are 6 of them. we got 3s2, and then 3p, that's the third one over. And so we have to go back and write 1s2, 2s2, 2p6, 3s2, 3p3. Okay, let's go and just do neon while we're in the groove here. So here is neon. Neon's going to be 1s2, 2s2, 2p, and it's the sixth one. So 1s2, 2s2, 2p6. Let's look at beryllium. Beryllium happens to live here, so it's 1s2, 2s2, and that's it. Oops. 1s2, 2s2. Okay, fluorine. Fluorine's right here, so we're going to go 1s2, 2s2, 2p, and it's the fifth one. 1s2, 2s2, 2p, and this is 5. And then finally potassium. Potassium's right here. 1s2, 2s2, 2p, and there's 6. 3s, there's 2, 3p, 6, and then 4s, and it's the first one. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. That's it. Okay, let's do orbital filling. So for phosphorus, remember, whenever there's an s, there's one line. So we're going to call this 1s, and there are 2 of them. Okay, 2s, and there's 2. Anytime there's a p, you draw 3 lines. We're going to label the middle one 2p, and they fill like this. Up, 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 and then they pair up, down, down, down. Okay, then we have 3s2, and then 3 lines for 3p, and we're going to go 1, 2, 3. Okay, next one, neon. So we have 1s2, 2s2, and then 2p6. We're going to draw 3 lines, 2p, and we're going to go up, 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 down, 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 and then that guy's full. Beryllium, 1s2, 2s2. Let's see, fluorine, 1s2, 2s2. I'm going to draw 3 lines, 2p, and we're going to go 1, 2, 3, 4, 5. For potassium, 1s2, 2s2, 3 lines for 2p, and we're going to go up, 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 down, down, down. There's your 2p6, 3s2, 3 lines for 3p, and we're going to go up, 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 down, 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 half fill, right? And then finally the last one, 4s and 1. So for the number of valence, we're just looking at the ones in that outer energy level, right? And so you can look at the diagram and see them, or you can also just look at the periodic table. You know that these all have 1, these have 2, these have 3, 4, 5, 6, 7, and these have 8, right? So you can just count over if you want. Or you can look at the diagram, either the orbital filling or the electron configuration, and that will tell you as well. Okay, so looking at phosphorus, phosphorus has 5 valence electrons. These and these in the third energy level, 3 traveling planar and 2 traveling spherical. So if you're going to do a Lewis dot structure, you're going to start on the right and just put 5 dots. So right, top, left, bottom, and then back to the right. There's 5. Neon has 8. It's a noble gas, right? So 6 here and 2 here. So you're going to put the symbol neon and then just 2 on each side. 2 on the right, 2 on the top, 2 on the left, 2 on the bottom. Beryllium has only 2. So I prefer, if you do it, to do it like this. For fluorine, notice it has 7, 5, and 2. So we're going to put fluorine here, and it's going to go right, top, left, bottom, right, top, left. Okay, so 2 on each side except for the bottom, which only has 1. And then potassium only has 1, just that 4s1. So for its symbol, just 1 dot. Okay, pretty straightforward. Let's see. What are the valence electrons? Once again, we already said these are the ones in the outer energy level. The ones on the outside. How can you determine the number of valence electrons using the periodic table? We just looked at that, didn't we? Okay, so if you can count from left to right and skip that middle block, that D block, most of them have one or two. Most of them are two. Some of them are one. Some of them have different numbers. I won't ask any from the middle, but just count left to right. 1, 2, 3, 4, 5, 6, 7, 8. Easy. Okay, the only thing that's probably goofy here is I didn't tell you which groups these are, all right? And so I'm going to go through and name these, okay? This is going to be slightly new. So this group right here, group 1, right here, these are the alkali metals, okay? The group right next to it are called the alkaline earths. Now, just so you're aware, helium is not an alkaline earth. Helium is actually over here where it needs to be. So alkali metals are group 1, group 2 are alkaline earth. This middle section, these are called the transitions. Okay, if I ever mention that, that's the transitions. These groups don't have numbers. So they're 13, 14, and 15, or don't have names. They're just called groups. You know, if they're called anything, they're called the first element, the boron family, the carbon family, the nitrogen family. Even 16 they call just the oxygen family. There is a name actually. These are called chalcogens. Nobody says that. These are called pnictogens. Nobody says that. So, however, group 17, these are the halogens. Okay, so 17 are the halogens, and then group 18, these are the noble gases. I know I've mentioned that one. So in looking at these, it says, say alkali metals, how many valence do they have? They have 1. Alkaline earth metals, they have 2. Halogens we talked about, which is group 17, they have 7. Noble gases are group 18, they have 8. And then you guys also realize that is 8 minus helium, right? Helium only has 2. These have 8. This one has 2. It's the only element that really doesn't follow the pattern. Group 13 has 3. Group 16 has 6. Okay. Okay, so we're looking for the total number of electrons here. If you look at silicon, it has atomic number of, 14. So that means it has 14 electrons. Potassium, look at potassium, it has 19. And then oxygen, oops, wrong way. Oxygen has 8. And then it says, so we wrote the total, then color the correct number of electrons for each orbit. Okay, and then so we have to do the electron configuration. Let's do that real quick. Silicon is right here, so we're going to be 1s2, 2s2, 2p6, 3s2, 3p2. All right, so 1s2, 2s2, 2p6, 3s2, 3p2. Okay, let's do potassium. We already did potassium earlier, so I'm not going to go through that. We already know how to do potassium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. And then finally, let's do oxygen. 1s2, 2s2, 2p4. It's the fourth one over. 1s2, 2s2, 2p4. Okay, and then just when it says color them in, what I would do is just do so. Kind of like when we do the Lewis dots. The only thing that's different is I spread the first 2 out. I don't know. I just like it aesthetically. It really doesn't matter. And so let's see. Then the second energy level, there's going to be 8. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. That one's filled. And now we need 4 in the third energy level. So we're just going to spread these guys out. 1, 2, 3, 4. Awesome. Okay, for potassium, same thing. So you got the 1s2. We're going to spread those guys out. The second energy level has 8. The third energy level also has 8. And then the fourth energy level has a single one. And then oxygen, we're going to spread these 2 guys out, and then we have 6. So we're going to go 1, 2, 3, 4, pair up 5 and 6. That's it. You guys are ready.